Good morning and welcome to section 16, sorry, 7-9. 7-9, we had done most of chapter 7, but we left 7-9 because it's a really important graphing section. Okay, so I'm going to go through these notes. This is on page 202 of your packet. You may not have the packet yet. You probably don't have the packet yet, but we will send this out to you. There's a link to it on your assignment sheet. Okay, so you can either just follow along with what I'm doing, or if you can print that one page out. Okay, graphs of rational algebraic functions. Okay, a rational algebraic function is something where you've got a ratio of two different functions, p of x and q of x, which stand for polynomials. And you have one of them over the other. So graph this on your Inspire. So there's a polynomial on the top, a polynomial on the bottom. Okay, so that's a linear monomial on the top, a linear binomial on the top, quadratic trinomial on the bottom. Okay, so to graph this on your calculator, we're going to go to our calculator. I'm going to add a graph, and we can do a control divide. And we've got x plus 2 on the top, x plus 2 on the top, and on the bottom we've got x squared minus x minus 6. So x squared minus x minus 6. And if you graph it, you can see it looks like this. So you've got this graph, okay? We will transfer this to our worksheet in a moment, but for now, just look at the graph and answer the following questions, okay? So if you're looking on your worksheet, question is, as x approaches 3 from the negative side, okay, that's from the left side, the graph shoots off towards infinity. In which direction? Okay, let's go back to our graph so we can see. You can look at my arrow. Here's where x is 3. X is 3 right there. So it looks like the y value when x is 3. I'm sorry. That's x is negative 3. When x is 3 is over here. So it looks like when x is 3 to the right, it looks like you don't have a value in your function. Let's just double check that. Okay, remember how to do a trace, which is menu 5, 1, graph trace. And now when you're in this mode, you can type in any value you want. I can type in 0, hit enter. And it gives me when x is 0, y is negative 1/3. I can type in a 1, hit enter. When x is 1, y is negative 0.5. Okay, I can type in 2. But really, we want to know when x is 3. Okay, so when x is 3, it looks like our function is undefined. Okay, so I'm guessing when x is 3, that's going to make this denominator equal to 0. 3 squared is 9. 9 minus 3, 6. 6 minus 6 is 0. So sure enough, our function's undefined when x is 3. Okay, but as x approaches 3 from the left, so from the, what does it say here? From the negative side. So as x is following this graph, approaching an x value of 3, but approaching 3 from the left side, they tell us our y value is approaching infinity in the negative direction. Okay? And the next question is going to be as x approaches 3, but coming from the right side or the positive side, our y value or the value of our function is approaching infinity in the positive direction. Okay, so let's fill out those two questions. X approaches 3 from the negative side. Graph, or the value of the function, shoots off towards infinity in the negative direction. And as x approaches 3 from the positive side, the graph goes to infinity in the positive direction. Okay, now I want to go back to the graph for a second because I want to analyze that just a little bit more. If we're approaching 3, remember I'm still in trace mode. You can see up here I'm still in trace mode. Sometimes you can't see it. It's harder to tell. So let's type in a value close to 3, but a little less than 3. So we can start with 2. When x is 2, we've got negative 1. How about 2.5? So we're picking x values as the x values get closer and closer to 3. 2.8, 2.9. We can get really close to 3, 2.99. And what's happening to the y value of our function? It looks like it's getting more negative. 2.999. Okay, we're getting smaller and smaller. Okay, so as our value x approaches 3 from the left side, our y value is going to negative infinity. Now let's go back. Let's go to the right side when x is 4. When x is 4, our y value is 1. Now let's approach 3. Instead of being at 4, let's get closer to 3, but from the right side. So 3.5. Our y value is now 2. About 3.1. Our y value is now 10. What about 3.0005? So we're getting closer and closer to 3, but from the right side, staying to the right side or the positive side of 3. And our y value keeps getting bigger. Okay, so just another way that you can see that. Let's go back, change our window back. Window zoom, let's go back to a standard window. Okay, so we can see our graph. Okay, let's go back. A less dramatic feature, a small gap or hole shows up at x equals negative 2. What the heck does that mean? When x equals negative 2. Zoom in on your graph. We're not going to zoom. We're just going to take a look at it. Use the graph trace to see what happens at x equals negative 2. Okay, so let's look. It looks like, before we use the trace function, when x is negative 2, it does look like our y value is a little bit negative. Not quite negative 1, not even negative 1/2, but it looks like it's a little bit negative. Let's go back to graph trace, menu, 5 for trace, and 1 for graph trace. Now we're in trace mode, so we can type in any value we want. Let's type in negative 2, hit enter. Okay, this is odd. When x is negative 2, our function's undefined. It kind of doesn't look undefined. It looked like there's a value there. Okay, let's look at what happens to our graph close to negative 2. Like, how about on the right side of negative 2? So instead of negative 2, negative 1.9. So negative 1.9, hit enter. Okay, negative 1.9. We're pretty close to negative 2, and it looks like our y value is about negative 0.2. That looks about right. Let's get closer to negative 2. So maybe negative 1.99. Okay, that's defined. It's defined when we're close to negative 2. It just wasn't defined when x was, when x was negative 2. If we type in negative 2, it's still undefined. But how about negative 1.99999? Oops, negative 1, negative 1.999999. Okay, well, that's defined. So it looks like it's only undefined at negative 2. Okay, it was also undefined when x was positive 3 and when x was negative 2. Okay, and it looks like our y value is going to be pretty close to negative 0.2. Now let's look on the other side of negative 2. So to the left, or the negative side of negative 2. How about negative 2.00, oops, 0.0000001. Okay, well, that's defined, and it also looks like it's about negative 0.2. Okay, so let's go back here and figure out why that's happening. Zoom in on your graph, use the graph trace to see what happens at x equals negative 2. When x equals negative 2, function is undefined. When x is negative 2. Okay. Now, if you trace x equals positive 3 and x equals negative 2, the inspire shows no value of y. Remember, it showed that vertical dotted line because the division by 0 in these, or because of the division by 0 at these values. Evaluate the function at the values of x algebraically to see what happens. Okay, so we're going to go to this function right here and say, what is f of negative 2? Well, you're going to get negative 2 plus 2 on the top. We're plugging in negative 2 for x, then plugging in negative 2 here. So negative 2 squared minus negative 2 minus 6. The numerator we get 0. The denominator we get 4 plus 2 minus 6 which is 0 over 0. Okay, we get something that's 0 over 0. We call that indeterminate form. Indeterminate form. Okay, it's undetermined what that value is going to be, but we know it's undefined because you can never divide by 0. Okay, let's plug in 3 into our function. So we're going to plug in the 3 up here, 3 plus 2 on the top. On the bottom, we get 3 squared, which is 9, minus 3 minus 6. We're going to get 5 over 0. Okay, this is not indeterminate form. This goes to infinity. Okay, it's undefined, but goes to infinity. We can't say it equals infinity because infinity is not really a number. It's more of an idea or a concept, something that's infinitely large. And that makes sense. If you think about what happens when you're dividing numbers, if we had, let's say, 5 divided by 2, well, that's 2.5. 5 divided by 1, well, that's 5. 5 divided by 0.5. When your numerator or your denominator gets smaller, but your numerator stays the same, your value, you're dividing by a smaller number, so your fraction gets bigger. 5 divided by 1/2 is 10. So when you get 5 divided by like 0.1, that's 5 divided by 1/10, which gives you 50. So when you get 5 divided by 0, notice if your denominator is getting smaller, your fraction's getting bigger, and this thing's actually approaching something that's infinite. Okay? Now, let's sketch the graph above. At both x equals -2 and x equals 3, the graph has a discontinuity, a value of x that makes your function undefined. The discontinuity at x equals -2 is called a removable discontinuity, okay? Because you could define f of 2 to be a value that fills in the graph, and I'll talk about that in a second. The discontinuity would be, quote, removed, okay? The discontinuity at x equals 3 was a vertical asymptote. Okay? The graph never crosses the vertical line. At x equals 3, the graph cannot be made continuous here. So a vertical asymptote is a discontinuity that cannot be removed. Okay? Let's look at this thing. Let's go back to our function. Okay, let's plot some values. So how about, I'm still in trace mode. So -5. We've got -0.125. So I'm going to put that on the graph. See that really small. Okay, we set at -2, we were undefined, but we were going to get something really close to, let's say, -1.9999. Our y value is about -2. So we're going to plot a point near there. -2, about -0.2, but that doesn't exist. So I'm actually going to put an open circle there, okay, to show that there's actually an open spot, basically a hole or a removable discontinuity in the graph. Okay, let's check when x is 0. Our y-intercept is -1/3. Plot a couple more points. When x is 1, we've got -0.5. When x is 2, we've got -1. And then when x was 3, we have an asymptote, okay? So we're going to draw our asymptote in here. We draw a vertical dotted line, okay, to show that our function keeps getting closer and closer to that line but never touches it. Let's pick a point, 2.5. -2. So at 2.5, we're at -2. I'm going to have to keep going. We've got the idea of our graph, okay? It looks like our graph never crosses the y-axis. Down like this. And this thing right here is an open circle, okay? that open circle, for right now, we're guessing that open circle was at -2. And it was about -0.2. We're going to verify that in a moment. Okay, now let's go to the other side of the graph. How about at 3.5? And we've got 2. 3.5 comma 2. How about at 4? Oops. We've got 1. At 5, we've got 1/2, and so on. So our graph is going to look like this. Okay, and this asymptote, our graph gets closer and closer to the asymptote, but never touches it. Okay. We could, it says on the bottom, create a table of values. You can make a table of values. Find values close to x equals -2 and x equals 3, preferably on each side of -2 and in each side of 3. Okay. Now, algebraically, let's look what happens algebraically. Okay, factor f of x below. So our f of x function looked like this. X plus 2 over x squared minus x minus 6. So x plus 2 over that factors into x plus 2, x minus 3. Okay, that's our graph. And here's where you can see more clearly where our discontinuities are going to be. Discontinuities are any values of x that cause your denominator to be 0. So there will be discontinuities at x equals -2 and x equals 3. Okay. Now, canceling the x plus 2 factors, and we end up with 1 over x minus 3, removes the factor that makes the denominator go to 0 when x is -2. The removable discontinuity has been removed algebraically. Okay, so watch what happens. If we're going to graph this thing on our graph, let's actually graph this thing on our graph. And the nice thing about the graph, we can hit the tab, and we're going to just graph our new function, 1 over x minus 3. Okay, I'm getting the 1 over x minus 3. We first graphed this thing. Now we're graphing this thing. These should basically be the same function because we canceled x plus 2 over x plus 2. The difference is in this version, our function's not defined. There's a discontinuity when x is -2. In this function, x equals -2 is not a problem. It doesn't make your denominator 0. So let's compare the two. This one I'm going to do in blue. This one I'm going to do in red. Okay, it just automatically puts the next one in red. So let's do a control divide. And we've got a 1 on the top and an x minus 3 on the bottom. And you can see that graph's now in red. Now, let's do our trace again. Menu 5, 1. Okay, let's look. Now watch what you can do here. So let's say when x is 1. When x is 1, you can see on, just gonna move that out of the way. When x is 1, y is 0.5. Now to jump to my red graph, now notice I'm on the blue graph. You can see that's blue, this is the blue graph. If I jump to the red graph, I just arrow up or arrow down. So I can do an arrow up. Notice now I'm on the red graph. It has the same y value on both graphs, okay? Arrow up, arrow down. Red graph, blue graph. The 2 points are identical. And that should be the same for pretty much every point. Red graph, blue graph. Okay, now let's go to -2. Enter. On the red graph, -2 is not a problem. And our y value is, in fact, what we said. So we just verified that our y value is actually -0.2, which we guessed when we looked at, arrow up, the blue graph where it was undefined. We couldn't plug in -2 because on this graph, value of -2 makes your numerator and your denominator 0. So if it makes your denominator 0, it's going to be undefined. Okay. Now, when we got rid of that, we canceled those factors that caused the problem. Now we're on this graph, and we can see where that point would have been if that -2 were not a problem. Okay. Okay, let's go back here. On the other hand, there's nothing in the numerator to cancel the other factor, the x minus 3 factor. in the denominator. So the discontinuity x equals 3 is not removable. It's only a removable discontinuity or a whole if it's something that cancels from the top and the bottom. Okay, so let's look at this summary of what we just learned. If a value of x equals c makes the denominator of a rational function equal to 0, then there is a discontinuity. It could be one of two types. It could be a removable discontinuity, or it could be something that causes a vertical asymptote. And how do you know the difference? If f of c has the form a non-zero over a 0, then there's a vertical asymptote. A non-zero over 0 gives you something that's infinitely large, which we just looked at on the first page. Okay. If that non-zero is positive, then this thing's going to positive infinity. If that non-zero is negative, this thing's going to negative infinity. If f of c has the form 0 over 0, which we noticed over here, 0 over 0, and that happened because we were able to remove or cancel one of our factors. Okay, then we have it's said to be indeterminate. To determine the behavior at x equals c, simplify the fraction, which we did up here. We simplified. We factored to see whether or not the division by 0 has been removed. We factored, we canceled, we simplified, it's been removed. Then evaluate the reduced form at x equals c to find the y-coordinate of the removable discontinuity. So for instance, f of -2, we're now going to plug in -2 into this one, where we've gotten rid of that discontinuity. So it's going to be 1 over -2 minus 3, which is -1/5, which is what we got, -0.2. Okay. Now we're going to do some practice on this. Describe the vertical asymptotes, removable discontinuities for the graph of each rational function. A vertical asymptote, this is important. That's an equation of a line. You have to give me the equation of a line. Removable discontinuity, that is an ordered pair. It is one single point. Okay. So here, the only discontinuity is when x is -2. Now, is that a vertical asymptote or a removable discontinuity? Well, it's a vertical asymptote because this thing doesn't cancel with something up here. So the vertical line is going to be the line x equals -2. Make sure you get that in equation of a line. Removable discontinuity, there's none. Okay, next one. Does anything cancel? No, these are not identical factors. There's one removable discontinuity at x equals -5. Is it a vertical asymptote or a removable discontinuity? Well, it doesn't cancel, so it's a vertical asymptote. X equals -5. It's the equation of that vertical line. Removable discontinuity, none, because there are no factors that cancel. Okay, let's go to this one. Vertical asymptote, removable discontinuities. Here there's two discontinuities. And when x is -3, that's a problem. When x is +1, that's a problem. Okay, so this one, x minus 1, doesn't cancel. So that means the value of x that makes the denominator 0 is x equals +1. Since it doesn't cancel with anything, that's a vertical asymptote. Now, the x plus 3's, we can cancel those. And we end up with 1 over x minus 1. Okay, but that means since that canceled, we know there's a removable discontinuity at the x value. That's a problem. The x value that's a problem would be -3, because -3 plus 3 would be 0. And this is a removable discontinuity or a whole. It's a single point, so you must give an ordered pair. The y value, well, we can't plug in 3 into here. We'll get 0 over 0. Right there, we get 0 on the top, 0 on the bottom. We're plugging it into the simplified version to see what the value would have been if there wasn't a whole. Okay, so we get y value is going to be 1 over -3, plugging in the -3 for x, minus 1. That's 1 over -4 or -1/4. Get the hang of it? Okay, we'll do the last three real quickly. What cancels? The x minus 2's cancel. If it cancels, that's a removable discontinuity. Oops, sorry, not -2. That should be +2 because it's the value of x that would make your denominator 0. Now your y value is going to be what you get when you plug that 2 into the simplified version. So after we cancel those, we get an x plus 3 over x plus 1. So we're going to get a 2 plus 3 over 2 plus 1, which is 5 over 3. Okay? The vertical asymptote is the value that makes your denominator 0 that doesn't cancel. So that's x equals -1. Again, a vertical asymptote is a vertical line. Give the equation of a line. Removable discontinuity is an ordered pair. It's a single point. It's like you took one point out of your graph and removed it. Okay? We're going to simplify. We're going to factor x minus 2, x plus 2, x plus 2 on the bottom. Okay, there's only one discontinuity, one value that makes the denominator 0. This factor cancels, so it's going to be a removable discontinuity at -2. Okay, plugging in, once we cancel these, this thing simplifies to x minus 2. So we're going to plug in the -2, and for x, -2 minus 2 is -4. A vertical asymptote, there were none. Okay, and the last one, let's see if we can factor x plus 2, x minus 1. In the denominator, we've got x plus 2, x plus 3. Those cancel. When you simplify, you get x minus 1 over x plus 3. If it's something that cancels, you get a removable discontinuity at x equals -2, because that would have made your denominator 0. We're going to plug in -2 into what's left after we simplify. So this y value is going to be -2 minus 1 over -2 plus 3. So -3 over 1. Right. This one does not cancel. So when x is -3, you have a vertical asymptote. Okay. Thank you for watching. I hope that was useful, and I will see you all soon.